Welcome back to the world of equilibrium. Let's do some example problems. All right, so on the notes, I'm now going to work through all of these example problems, and there are many variations. I tried to give the most obvious ones or the most used ones. Okay, let's just determine the answer to these problems, and hopefully you'll get a feel for what type of question you're going to use for each kind of ice table. Okay, so here's just my little reminder. Tabulate the known initial and equilibrium concentrations, come up with a change, use stoichiometry. So basically use the ice table. All right, problem number 1. A mixture of 5.00 times 10 to the minus, a little too high, 3 moles of hydrogen and 1 times 10 to the minus 2 moles of iodine is placed in a 5-liter container at 448 degrees and allowed to equilibrate. All right, first step has not changed. I need a balanced chemical equation. Balanced chemical equation. So right now I know the two reactants. If I don't recognize this equation, I'm going to look for the product. And there it is. Analysis of the mixture shows the concentration of HI. So I'm not going to play with those numbers yet. I'm going to, let me see. So I told you it was H2 plus I2 is in equilibrium with 2HI. And granted, I know that was already written, but from the problem, I gleaned that data. Okay, in the future, there'll be a lot of them that you're going to have to be able to figure out the products on your own. Some redox reactions, lots of metathesis reactions, eventually just acid and base reactions. But if not, you're supposed to glean that information from the problem. Okay, so there's my balanced chemical equation. Well, what is the next thing I do? I look up I can't believe I just said that. Jumping ahead of myself. HI, you write the equilibrium expression. And then you ask yourself, is this a K I can look up? And in this case, that is not an equation that I gave you equilibrium values for. And it's at 448 degrees. So even if it was, I couldn't have used the values. And yes, you could go look that number up first before writing out the equilibrium expression. I'm just trying to stay in order. Okay, I have my balanced chemical equation. I have now an equilibrium expression. I cannot find a K, so let's fill in the table. A mixture of 5.00 times 10 to the minus 3 moles of H2. Now, the first thing I recognize is that is not a concentration. That is just the number of moles. So do I know the volume that all of these are going to be mixed in? And they are all placed into a 5-liter container, and these are gases. So the final volume will be 5, as long as they can't escape, which we're going to assume. Oh, okay. Well, if I want the concentration of the hydrogen, then I'm going to take the moles and divide it by the final volume of the solution. I'm going to do the same thing for I. All right, now let's look at that HI number. Analysis of the mixture shows the concentration of. So that one's already a concentration. I just need to worry about these two. And 5 to the negative 3 divided by 5 is 0.00100 because I get 3 sig figs. Check. Okay, and the next one, 1 to the negative 2 divided by 5. Do a check. All right. Those are my concentrations, but which concentration are they? So we're going to go back to the problem. oh, this is what I mixed together. And because I took into account the final volume, these amounts are already diluted. So 0.00, how many zeros do I get? Yeah. So there's the hydrogen and the iodine. Now, I'm going to go back to the problem. A mixture of hydrogen and iodine is placed in a container and allowed to equilibrate. So I did not put any HI in initially. And I know it's going to change based on its stoichiometry. And if I do the calculated values, it's going to be that one, that one, and over here it would just be 2x, but I gave you 1.87 times 10 to the minus 3. Now, if that bothers you to put the equilibrium value on the same line as the ones that I got from the table, definitely make two lines, one for calculated from the table and one for given. But as long as you keep them separate in your mind so you know which one and when to use it, that's absolutely fine. All right, and now the question is, I filled out my table. Let me see, calculate Kc and Kp for the following reactions. Oh, so it is asking me to calculate that value. So do I have equilibrium concentrations of HI? Yes. Do I have it of H2 and I2 yet? Ooh, no. So that's three variables. So I can't solve that, at least in this class. And so I must be missing something. So let's go to the table. Did I give you a way to find X using just the data from the table? And oh, look, I did right there. Because 0 plus 2x is equal to 1.87 times 10 to the minus 3. Divide both sides by 2, and the answer wrong. Here we are, is 0.123123, and I get 3 sig figs, so 935. Confirm here. All right, and it's confirmed. All right, what in the world am I going to do with that X? I'm going to go up here and I'm going to take A and B, or in this case, hydrogen and iodine, and I'm going to subtract it so that I can find the equilibrium value. So 0.123935. And as far as sig figs are concerned, this is an addition and a subtraction. So 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. You only get to keep 5 after. All right, let's plug those in. And 0.001, this value comes up 1, 2, 3, 4. And the bottom one comes up 1, 2, 1, 0, 6, 5. Do that again. All right. Those are my equilibrium concentrations, sig figs, but I only get to use the 6, so I'm going to round this up to 7 times 10 to the minus 1, 2, 3, 4, 5. So this is 7 times 10 to the minus 5. What? Only one significant figure? I know it. Love to hate them. 1, 1, 2, 3, 4, 5. So I get to only keep, round that up. So it's 1.07 times 10 to the minus third. All right. Don't forget your molarities. Now let's plug those in and find our Q. Oh, or our KC. Oh, or our KP. Okay, it's very important to know what are you plugging in and what are you finding. Are these initial concentrations like we did before? No, so it's not the Q. Are these concentrations, molarity? I could put Kc, or if they're all pressures, I could put Kp, and these all happen to be in molarity, so I can find my Kc. So K subscript C is equal to 1.87 times 10 to the minus third squared all over 7 times 10 to the minus fifth times 1.07 times 10 to the minus third. You know, there's something about that number that's just bothering me. I'm going to check it one more time. So 1.87 to the negative third, and I'm going to divide that in half, which is 3 zeros, 935, 3 zeros, 935, and then I'm going to subtract that from 0.001, which is 1, 2, 3, 4, 6, 5, 1, 1, 2, 3, 4, 6, 5, and the other one, 0.002, is 1, 2 zeros and a 1065. No, okay. Should trust it. All right, calculate those out. So 1.87 to the negative third. I'm going to square that, divided by 7 to the negative fifth, and 1.07 to the negative third. Ooh, 46 points, lots of numbers. So I'm not rounding yet. So 46 point, if I just go to 1 after, it would be 46.7. Do a confirm, 1.87, negative third squared, and 7 to the negative fifth. Divide by that, and divide by 1.07 to the negative third, and I end up with, yep, same value. Okay, so my value of Kc came out to be 46.7. I am only allowed to keep one digit in my significant figures. So I only get 5 times 10 to the first. Okay, so that is the value of my Kc. And if I want the value of Kp, I'm going to plug it in. So Kp is equal to Kc, which is, I'm going to plug in the 46.7 and then take care of the sig figs in a minute. And RT, so 0.0821, and the temperature is 448 degrees C, and I need the change in the moles. So there's 2 moles of gas on the product side, and there's 2 total moles of gas on the reactant side. So in this case, it's 0. That goes away as the big number 1. So in this case, Kp is also 46.7, but you don't get to keep that many sig figs, so it's 5 times 10 to the first. All right, there is a fairly long problem that gives us most of the details in following an ice table. Step number 1, balanced equation. Step number 2, equilibrium expression. Step number 3, fill out your ice table with what is given. Step number 4, what in the world are you looking for? That's really the interesting point. Did I give you information so you could find x from the table, or are you going to have to plug them all into the equilibrium expression? And that's why the problems look like they're unique. None of them are unique. They're pretty much the same problem over and over and over. It's just which variable or which piece are you looking for? All right, and that was problem one. Until the next time, jolly out.